Structural engineering principles, looking at the shear force diagram. First up, what I want to do is I want to look at my beam. I'm starting from the left, and anything upwards is a positive and anything downwards is a negative. I'm using my positive shear principles just in case you want a picture for my head. So as I go in 1 meter increments, I'm going to look to the left and I'm going to say whether something's going up or down. This is how we do it. Okay, so I've got, I'll start with 9 meters. You know, my plane distance from the left is 1 meter, 2 meters, 3 meters, all the way up to 9. At 0 meters, there's nothing happening. There's no points, there's nothing, so it's 0. Then I move on and I say, well, actually 1 meter in, I've got this 44 kilonewton going upwards. So that's a positive, that's a plus. But I've also got, just before that was the 0, was the nothing. So I've got to make sure if I've got a point load that's on a meter, so it's actually smack bang there, I've got to make sure I clearly show that. So I have 2 values. Wherever there's a point load, you have 2 values of shear. You have the 0, which indicates just before it, and then you have the 44, which is just after it. It's a positive shear that way. Yeah, lovely. Then I move on. And at the next meter, I've got 50 going in the opposite direction. This is a negative shear. So I'm going from a positive shear here, plus 44, to a negative because I'm adding that minus 50 because it's pulling down, it's pushing it down at that point. This is a vulnerable spot, isn't it? Because I'm crossing the 0 axis. I'm going from, oh, okay, I'm sort of got a lot of force in this direction, and suddenly straight after it, I'm going 50 kilonewtons in the opposite direction. So that could cause a bit of ripping. That's a bit of a worry. But those values are indicated here. Okay. Yeah, and then I move on to the 3rd meter in, and I look to the left and I've got plus 44 minus 50, so I've got this minus 6, so I've just got a shearing force of minus 6 at that point. And then meter 4, you just keep going, and don't forget, whenever you've got a point load, you have to add just before the point load and just after the point load. And if it's massive and if it crosses the x-axis like it does here, the y-axis. Oh, the x-axis is the x-axis. If it crosses that, this is a point to worry about. This is where it goes suddenly from one extreme to the other, positive to negative. It's pushing downwards, suddenly pushing upwards. So that is where you might find that the beam will have issues, and you've got to think about supporting it. And then you just keep going. All right, so hopefully that makes sense. I'll move on to the bending moment one. So we follow the same principles. You work from the left and you make your way through. But the difference between the shear force and the bending is that the bending moment is force times distance. So if you have a look here, 0 meters in, there's nothing going on. 1 meter in, instead of having that line upwards saying, oh, I'm going from 0 to 44, you're using the momentum. There's no momentum at this point because you're sitting on the point. Like the 44 kilonewtons is at that point. It's not causing it to bend, it's just sitting on top of it. So you'd put 0 times 44, which would cancel out that, which means that the 44 is no longer relevant. The 44 becomes relevant another meter in, where you have to times it because that is now causing momentum. The 44 is 1 meter away, so it's causing this bend, this pressure for it to bend. Okay, and as you can see, the 44 follows its way through, and I would suggest this is how you do it. You would just, once you hit a point like this, 44 kilonewtons, I would be doing 44 times 1, 44 times 2, 44 times 3. So every single meter that you are a step away from that 44, you make sure you add those in. You can just copy and paste and just add another meter on. And then you're just timesing the 44 by the meterage, how far away it is from the point that you're looking at each time. And then again, this has got 50 kilonewton, it's going in the opposite direction. But again, it's not causing any issues right now because, again, it's not causing momentum because it's sitting on that point. So 50 times 0 is nothing, so it's not even included in here. However, a metre away to the next point, that 50 then becomes relevant. And you would do the same thing, 50 times 1, 50 times 2, 50 times 3, 50 times 4, all the way down here. So that's included there. And you would just do the same here. So the point load of 30 comes in as well. Not relevant at the point that it arrives, but a metre in, very relevant. And again, you see how this goes from positive bending to negative bending. Again, this is a point to concern ourselves with, because you're bending it in one direction and suddenly you're bending it in the other direction at this point. So where this graph crosses the x-axis, we've got to worry about that. Got to have a little think about that. May need a bit of support. Okay, and then you just keep going. Now, when it comes to the universally distributed load, what you have to do, I think you can see it in here in this point, you at every metre, so if you imagine there's 1 metre, so at this 76, but so at this point here that we're talking about, before that there was nothing. Over the course of that metre, it's had 10 kilonewtons applied to it. Okay, so there's been 10 kilometers applied, but the distance from this point that we're trying to calculate from is half of that whole UDL, universally distributed load, right? So you put a point in the middle, which is, and then you say, well, actually, half of 1 metre is 0.5, and that's what you're doing there. The distance is halfway between that UDL, so that half of that 1 metre. If you move on then and you look at this, the universally distributed load, it's the same. It's not the same value, sorry, it's 10 kilonewtons per metre. So if you've moved in 2 metres, that is then 20 kilonewtons, isn't it? So that's what the 20 is, so 10 times 2. I've kind of done it here, so I've done the distance, so it's 10 kilonewtons times the distance from the UDL, so how many metres you're into the UDL, but then you've got to times it from distance from the point that you're calculating it, and that's half of the edge of the UDL. So half of 2 is 1, half of 1 is 0.5, half of 3 is 1.5, half of 4 is 2. So that's how I would write it so that you get it in your head correctly. If you're worried about the UDL, look at the I've done a video on UDL as well, how to work that one out. Okay, and then you just keep going, and there you go, there's your bending moment diagram. So table form, graphical form, whatever you find easier, bit of both. I do both just so I can check my calculations. This can all be done on a spreadsheet, and it will produce a graph for you. Okay, thanks, take care, bye.